Eh ben, c'est parti. So thanks to assist to the seminar, biocomposite based on PLA and bioactive glass fillers for bone regeneration. A project supervised by Jean-Marc Chenal, Abdelrahim Mazouz, and Khalid Lamlawar. Jean-Marc Chenal from Matéis and Abdelrahim Mazouz and Khalid Lamlawar from EMP. Okay, this presentation will be divided in 3 parts. First, I will present the interest of using biocomposite with a resolvable matrix and bioactive filler. Next, I will present a study elaborated at Matéis and EMP about the effects of thermal treatments and particle size of bioglass in this kind of biocomposites. And in the second part, I will finally explain the effect of bioactive fillers and the process elaboration from bioactive fillers of different nature. Okay. For the context, osteosynthesis is a surgical procedure to repair bone fractures. To repair these bone fractures, we can use these osteosynthesis systems such as screws, plates, nails, or wires. In France, during these last 10 years, the number of this kind of operation increased by 9%. And these 3 different illustrations, we can see examples of repair systems, such as metal screw with an external fixation, a plate for maxillofacial fracture, or a plate for a cranial fracture made by 3D printing. Okay, but why choose a resorbable matrix and a bioactive filler? So non-resorbable implants like titanium, ultra-high molecular weight polyethylene, or PEEK can present several problems for this kind of applications, such as a fibrous encapsulation, a loosening, or realize several surgical applications during the treatment. The use of a resorbable matrix like a polyester combined with a bioactive filler like bioglass allows us to create a biocomposite which have an adequate rigidity, a good thickness, and it can be produced with classic processing with plastics. Okay, here I will present you some examples in literature. First of all, here we have an example of an in vivo study where we can observe the use of bioactive filler, which increase the rate of bone formation. Here we have the use of 5% of bioglass, which increase and promotes the bone regeneration around the implant. And here on the other side, we have an in vitro study who shows that bioglass can stabilize the pH of the solution. This effect could reduce a possible inflammatory response already observed during the implant of the systems. Okay, here we have another 2 examples of in vivo and in vitro studies. And this study relies in Matéis, shows a faster absorption of PLA bioglass than just a PLA implant, and also shows that this bioglass promotes the bone formation around the surface of this implant. And finally, here we have a cellular study which confirms that PLA bioglass shows a superior biological response and osteoactivity induced properties than PLA or PLA with hydroxyapatite. Even here, if PLA bioglass had the worst proliferation response, and there was not a huge difference with the other samples in the study. So why we choose a PDLLA for our study. In the family of aliphatic polyesters, PDLLA show a low inflammatory response thanks to the non-crystallinity, and also it has a interesting degradation time and a mechanical properties which are close to them of the cancerous bone and cortical bone. Here we can see also the PGA, who degrades very fast, and it's inadequate for osteosynthesis. However, the combination of this PGA with a PLA can modulate the degradation time of the polymer. Okay, so in literature, they also studied the mechanical behavior of these two kinds of biocomposites, PLA with hydroxyapatite and with bioglass. And here I will present you two examples who elaborate the samples with the same process, injection molding. And in these two studies, they observe the evolution of these mechanical properties, tensile strength, and elongational break and modulus in function of the filler content. We can see that the temperature processing is different for each biocomposite. For PLA hydroxyapatite, it was about 118, and for PLA bioglass, 120. So we can see that the tensile strength and the elongational break decrease as the content increase, and the other side for the modulus increase in the both cases also, and when the content increase. So in the next part, we will see why the temperature was lower for the PLA biomass. So in Matthijs and EMP laboratory, 3 people work on this type of biocomposites. In the following 2 graphs, I show you the results obtained by Nora Durgam and Eloise Perrin during her thesis. In the graph on your left, you can observe the evolution of the intrinsic viscosity as a function of the filler content. We can see that the viscosity decreases with the filler ratio, except for the biocomposite with the bigger particles and with a thermal treatment. And this effect could reduce the degradation and increase the mechanical properties of these implants. And in this other study made by Eloise, we can see an histogram who shows the evolution of this intrinsic viscosity for PLA with 30% of bioglass tip 45S5, and for a new bioglass developed in the context of this thesis. These colors indicate the value of the viscosity for the matrix alone in blue, in orange the preparation of the granulates, and green the injection molding step, and finally yellow the elaboration, the stabilization, the sterilization. We can see that the process degrades this matrix, but it was the sterilization who has a very important effect, and this process has to be more studied. Oh, okay, so during these 15 last years, the authors have shown the possibility of each process. I would like to show you just a list of different processes and the authors who have taken and show an interest in them. They are from the classic plastic process, such injection extrusion, until additive manufacturing, such stereolithography for PLA and bioglass. And during my thesis, I will work in 3 different processes. One is extrusion, injection, transfer molding, which I will present you now. Another thermal sintering, and also fused deposition modeling. These processes will allow us to produce functionally graded materials, which will be a biomimetic approach to satisfy the requirements in osteosynthesis systems. So now in this part 1, I will present you the studies made in Matriz and IMP about the effects of thermal treatments and particle size of bioglass in PLA bioglass composites. In this study, we use a matrix of PLA and also a matrix of PP and bioglass particles type 45S5, who has 2 sizes, 3.5 micrometers and 440 to 500 micrometers, and also 3 kinds of thermal treatments. And these thermal treatments shown a modification of the crystalline structure of these bioglasses. So the composite was obtained by extrusion and milling the filament to obtain a compound which an excellent filler dispersion. The samples were produced by injection molding, and in this process, the elaboration protocol consisted in first drying and mix the base material. After this extrusion process with milling granulation, and finally the injection at low temperature. During this extrusion process, we had monitoring the torque of the twin screw to follow the evolution of the material at high temperature. So during the elaboration of this biocomposite, we obtained samples with an important signs of degradation, like yellowing, the presence of bubbles, amber coloration, a strong smell, and a lower torque values than the neat PLA. Here we can see it. These torque values correspond to the maximum values of torque observed during the extrusion process of the composite. And also, we observed that some biocomposites had a weak coloration, not bubbles, and a high torque values. So there was a relationship between the PLA degradation and this bioglass. So we took the samples that had the most signs of degradation, and by infrared spectroscopy, we observed the chemical bonds in the sample. So a peak absorbance band at 1600 can explain the chemical reaction that degraded our PLA. In fact, in presence of moisture, the SiO- on the surface of the bioglass are associated with the contrions that can provoke the rupture of these ester bonds of the PLA, which accelerate the hydrolysis of PLA. To quantify this degradation and to determine the composite with the best properties, we use 2 characterization techniques. The first one was oscillatory aerometry and the size exclusion chromatography. So the rheological study can be used as a tool to characterize the effect of bioglass on the matrix. The degradation is related to the loss of viscosity, and here in the first figure, we can see that the bioglass with the thermal treatment T3, okay, here, has the highest viscosity, and so the less degraded. From a rheological point of view, composites of bioglass and PLA doesn't show the behavior of fillet systems as in the case of polypropylene. When the filling rate ratio increases, like in polypropylene, normally the viscosity has to increase. But in fact, when the ratio increases, the viscosity decreases, showing that degradation effect is more important than the reinforcement effect with PLA and bioglass. So this size exclusion chromatography study was performed to obtain the molecular weight and value for each sample. As the chain scission is directly related to the molecular weight, this technique allows us to quantify the degradation of each sample. For example, here, for the samples at 50%, we can see that with the smallest particle size and without thermal treatment, we had a loss of molecular weight of 87%. And in the other side, with 10% of bioglass and with bigger particle size and with a thermal treatment like T3, we obtain only a 70% of degradation. Okay. We studied the mechanical behavior of these composites using a compression test on a cylindrical samples, and we followed the evolution of the stress at the yield strength as a function of the filler ratio, the bioglass content. We observed that as the filler ratio increases, the stress decreases, and the sample becomes more and more brittle, as shown you previously in literature. We also observe that the fracture normally occurs at the Louet and the filler matrix interfaces. Okay. An in vitro study allows us to observe the possible bioactive of our composites. At 50% field, we observe that the smallest particle size and without any heat treatment, they develop an hydroxyapatite layer in the surface of this biocomposite faster than composite with a low content of bioglass and with particles which has more crystallinity. On the other hand, even if it was more slowly for these biocomposites, all this confirm its possible osteosynthesis properties, showing an hydroxyapatite layer in the surface. So the elaboration at low temperature and the use of inert atmosphere allows us to decrease the degradation of PLA. This degradation was mainly due to the chemical reaction between bioglass and PLA. And to conclude this first part, I would like you to summarize the approach chosen to find and quantify the degradation of PLA. First of all, a monitoring step allows us to see this degradation, and the use of spectroscopy to determine the mechanism, and the size exclusion chromatography and rheology to quantify and select the less degraded composite. So. I will respond the questions at the end. No? Better maybe?
Yeah, yes, Xavi, I think in the end it will be better, yes.
Okay. So I will pass to the part 2. Here we present another study, this time using a direct injection molding. And I will show you different bioglasses and bioactive fillers. Okay, so here we have the same matrix, but this time with a filler of hydroxyapatite and with bioglass of 45S5, S53P4, and 72S, which has a different composition. Here we have 3 same images of hydroxyapatite, bioglass, and PLA microenzymes. Okay, similar to the first process, this one, but instead of green the extrudate, it's directly transferred to the injection machine. For the elaboration of my samples, I used the same procedure. First of all, I dried the base material. After extrusion in inert atmosphere, and this one direct inject, direct transfer to the injection machine at low temperature. This elaboration protocol allows us to reduce the residence time at high temperature and reduce the degradation by hydrolysis and simulate an industrialization process and obtain composite with a good dispersion. Okay. As previously done in the part 1, we mount the torque of the twin screw. Here we can see the torque in a function of time, and we have seen that the torque decreases in time, showing a degradation. The viscosity decrease in time, but not for the case of hydroxyapatite. Okay. So, as probably observed in the torque, here in the size exclusion chromatography, and the hydroxyapatite doesn't affect the matrix. In this study, we can compare the effects of hydroxyapatite, bioglass 72S and 45S5, and we can see that in the case of bioglasses, as probably observed in the monitoring, there was a loss of molecular weight, but it was more important in the case of 45S5. Why? Why? It's only due to the less erratic effect of the 72S. We can compare the results with them of the part 1 and see what's and see that for the 45S without thermal treatment, there was a lot of molecular weight of 62, and in our study it was 46%, and this difference is mostly due to the fact of use a process that's a direct injection. So we reduce the time at high temperatures, and so we reduce the degradation. So the dynamic time sweep presents like a tool to observe the behavior of nature and content of high temperatures. We can see that PLA at 150 degrees doesn't show any sign of degradation. Instead, for the bioglass composites, there's a decrease of viscosity from the beginning, And we can see that the degradation speed is faster in 45S5 than in the case of S53P4, showing fast degradation here than in the case of S53P4. On the other hand, hydroxyapatite and bioglass 72S shown a better response to time and high temperature. In the case of hydroxyapatite, the viscosity increase as the content of filler increase, and the viscosity remains stable during all the study. Not the case of the 72S, decrease, but much less than in the case of 45S. So the problem is that other kinds of neurology studies, like dynamic frequency SIP, are complicated to read because of the evolutive behavior of this this matrix. In order to reduce the experimentation time and simulate the thermal elaboration behavior, maybe a study test in linear and nonlinear regime could ask to obtain the results without huge or big degradation in the matrix during the experimentation. Here I show you just a possible example of a study to do with these evolutive systems. For the geometry obtained in the study and the low elongation at break, we decide to do a biaxial bending to obtain the ultimate tensile strength and the modulus of this kind of biocomposites. As previously observed by compression or tension, the strength decreased when the filler content was raised. Almost all the samples presented brittle behavior, but in the case of S53P4, for example, and they present better mechanical properties than hydroxyapatite. And I would like to ask you why, if the S53P4 are degraded, are presenting better properties than hydroxyapatite, even if the particles of bioglass were bigger than the hydroxyapatite. And maybe that's because here in these same images, we can see the interface and the adherence between the matrix and the fill, for in the case of hydroxyapatite and in the case of bioglass. And in these two images, we can see that there's a poor adherence between the fill and the matrix, who explains this mechanical response. And we can see here, in the case of bioglass, that there's part of PLA stuck in the surface of bioglass, and maybe that's showing better adherence between the matrix and the fill. So just for information, this to obtain these images, I took I have done a chiropractor at the biaxial bending fracture. So I crash in the fracture of the biaxial bending in nitrogen, and here we can observe what happened at the fracture of the biaxial bending test. So in this second study, we observe this poor adherence between the polymer and the fillers, and that even with using a injection process optimized, the samples had several signs of degradation. However, we obtained a really good particle dispersion with this process. And for the following studies, I would like to quantify this dispersion. For example, at this moment, I have the idea of use the degree of anisotropy of random cubes volume of my sample and compare it with a model who has the same content, and see how it evolves and compare it. So as observed in literature, and this type of material remains very interesting for bone regeneration applications. Tools like rheology will allow us to better control this degradation and mechanical properties of this composite. And the actual working studies are the thermal process at low temperature to prevent this PLA degradations, and a rheological study at non-linear regime. And we can see that there's a need to better understand this interaction with the matrix and the field and the mechanism behind this composite. So thanks to all.
So you're done, Xavi?
Yeah, I'm done.
Okay, thank you very much. I guess we can turn on the cameras, everyone, and let's have a discussion about this very interesting talk. Maybe Xavi, you want to take the questions in the order? You can open the discussion, and we can go step by step.
I will take step by step. So first one, 9. Okay. So this one, viscosity unusual decrease with the bioglass content because of the change season, enhanced degradation during the preparation. So yes, as I show you after in the presentation, there's a relationship between.
Yes, it was pretty clear that.
So yeah, it was responded here, I think. No,
you answered the question later in your talk. So yes.
Yeah.
Basically, when you put more bioglass, then you enhance the degradation. For some reason that we don't know, I guess, maybe. Okay, we'll see. Okay, so I asked the question. It was, I think you answered this question later in the talk, so there is no problem with this.
Okay. Yeah, we think, are you stop? No. We think that the mechanism behind this degradation is the fact of the presence of musculature and reaction in the surface of the bioglass, as I explained. And if we increase the content of bioglass in this kind of composites, there's more interaction between the PLA and the bioglass. So it increases the hydrolysis of this PLA.
Okay, well, thank you. You answered another question I asked also later.
Okay, so questions like 10, 12.
This was just a simple question about the fact that you didn't really show the processing route to make your PP-based composites. I was just wondering whether it was the same as the PLA or no.
Okay, the use of polypropylene, it was just to show what is the really behavior of a composite, the effect of the increase the filling, like here. It was just to, it was elaborated as the same with the same method as the PLA, but the purpose of use polypropylene was just to compare it in the dynamic frequency sweeps and show that by increasing the filler content, the viscosity of this biocomposite increases, showing the classical behavior and not the same as the bioglass with PLA, where this viscosity decreases due to the degradation.
My question was about also the molecular weight, like 250 kilogram per mole. Isn't it like very huge? Like, I mean, to me, it looks really big, but maybe it's just because I'm not familiar with PP. What's the temperature at which you do the extrusion?
So this first part, which I'm presenting, I didn't do it. It was previous studies, and I think that it was 119 degrees.
Okay. So it's enough to reduce the viscosity in the two screw extruder.
Yeah.
Okay.
I'm not sure. I think that it was 119, but I'm not really sure. But it was more like.
Yeah. Anyway, it cannot be much more than this, otherwise you burn everything. So. Yeah. Okay.
Okay.
I was asking this because when you have the TPE, for example, and you do extrusion, typically you have like 50 kilogram per mole. 250, it means that you have relaxation time that could be in principle extremely long, and so viscosity extremely high. So I assume that also the two screws extruder go rather slowly. Otherwise, then I think it's not possible really. You will have a torque which is far too high, or maybe it's the very big machine. I don't know. I was just curious about this.
Yeah. Also, they use a huge machine, so not like a mini injection or a baby plast. I think it was like a really injection machine. So what's the M distribution of size exclusion chromatography?
Here you show just the ratio of the average molecular weight. But if you reach degradation, then expect also a large broadening of the distribution. Might be of interest. I don't know.
I show the plot of the distribution of molecular weight.
Yes, but this is just the average molecular weight.
Yeah, that's just the molecular average. And in this study, I only have the average molecular weight, but in the others, in the second part, we will have all the distribution of molecular weight, and we will see the average in weight and in number, and how it evolves each content. But just for the presentation, I prefer to show the average and how it evolves. Showing the average, that it's more related to the degradation, no?
I mean, both. Yeah. I mean, it's good like this. I was just curious about whether you create like very small chains or eventually, possibly you may have branching also, but from the rheology you show, then apparently it's more chains scission. So I was just curious about the distribution if you had it, just to have a look at them. But okay.
Yeah. I have a.
It's very clear that molecular weight decreases and viscosity decreases. But there is I think no problem on this.
So I have it, but not for.
Yeah, it's fine. It's fine. You can show me later.
Yeah. So. It's interesting to degrade the PLA for the application in the body. If yes, what is the entropy we would like to reach to enhance the implant elimination? Okay. So the bioglass will enhance the degradation of PLA, and so the implant will degrade faster in the body, and it will take less than I show here. Really general example of 4 polyalphatic esters, and here for PDLLA it will be like 1 to 1.5 years to degrade it in human body, and using a bioglass it will really decrease this time, and so that reduce the reabsorption time. And yes, what's so the MW, the average molecular weight to reach the NMs of the implant elimination. I think just when it disappears, no?
No, I think it was very clear, your answer with this slide. I was really wondering, because you speak all the time about degradation, so I was thinking probably it's something I want to do. And in fact, this is something, of course, you're interested in. You want to make the degradation happening in the body. I think this is really nice. It's very original. It's like you put some filler, not to reinforce the material, but to accelerate its degradation. And so, I mean, never seen this before, so I was curious. That's really interesting.
So we want to increase the mechanical properties, but at the same time increase the degradation.
Yeah.
So, yeah. You have to find the technique to obtain implants with good mechanical properties and with a high content of bioglass to assure this bioactivity and a good biological response.
Mm-hmm. It's really nice. Okay.
Yeah. What's about the homogeneity of the distribution of bioglass particles and about the size distribution? So so here I show the this distribution of bioglass particles, and as I told you, I'm just starting to characterize this distribution of particle size, and I have the idea to try to use this degree of anisotropy, who's easy to calculate, easy with using imaging, and we can obtain a value of this anisotropy of different volumes. I was thinking about compare the degrees of anisotropy of random volumes from the initial volume and see if it converged to a value fastly or like it was really dispersed like here. I don't know I don't know if it's an easy technique to see this distribution, but
I had a question on that, Xavi. What is your model exactly? It's a random distribution of sphere. So red, the stuff you show.
This red is just just to suppose that we can try to elaborate a model of fillers in 3D, which will be well dispersed, and try to plot the degree of anisotropy and compare it.
Okay, because actually, if there is no anisotropy, it should converge to 0. So the fact that it's not to 0 means that there is an anisotropy at large scale.
Yeah.
No? It's not exactly 0 you get at the end when you have the larger volume.
Yeah, it's close to 0.1 for the for injection transfer molding.
So it means there is a slight alignment in one preferential direction in your volumes, but it's not so huge actually.
Yeah, it's not so huge. When you see the ellipsoid of anisotropy, really almost an sphere.
Almost a sphere, so it's not very anisotrope.
Yeah.
Okay.
But the thing was really to see if there were conglomerates or agglomeration of bioglass. And I was thinking to use the same technique as degree of anisotropy, but instead of use all the volume, use small volumes. For region of interest small, see if it's converged to a value or not. I don't know if I'm really explaining that well.
We can discuss that together. We'll really talk about that, but I think it's a good way to do it. But okay.
Okay.
Maybe Jean-Marc Pelletier, you want to discuss your question with Xavi, or it's fine? Okay. So Xavi, you can proceed, I guess.
Okay, no, it's fine for me. Just perhaps another question, if possible. Degree, your polymer is a semi-crystalline one or not? Because
no,
is so sorry.
It's not crystalline.
It's amorphous.
Yeah, it's amorphous.
Okay. No, because my question was: do you think that the existence of these spherical particles of glass may have some influence on the crystallinity of a material? So, but if it is amorphous, there is not a question. So sorry. Thanks.
Okay, no, you're welcome. So for slide 26, do we expect larger strains to enhance the degradation for a given formulation?
You see my point here?
No.
But if you increase the amplitude of the oscillation,
yeah.
So do you think that it will help to degrade the polymer?
I think that as we can see in the extrusion process, it's like we have an enormous shear rate in the twin screw, and it will accelerate the degradation. So in a nonlinear study, increasing the shear rate, maybe we could see this effect. Imagine increasing the shear rate, and after comparing for each time the viscosity of the modulus, and we could see a decrease of this modulus in function of the shear rate. Maybe.
Okay, might not be only the shear rate, but like the strain amplitude. But okay, shear rate is part of the problem. I agree. So you expect indeed that if you increase the strain, let's say strain amplitude or strain rate, then you help to degrade the polymer a little bit.
I think that as I didn't try it already, I cannot assure you that. But
what is your feeling?
My feeling is that if we increase the shear rate or the strain, we will accelerate this degradation, but I don't know if we could see it in rheology.
Yeah, with this I completely agree. Indeed, you could change conformation of the chains or the filler distribution, so you see a lower viscosity, not necessarily related to the degradation. I fully agree. And actually, I think also some chemical probes would be interesting. Like, do you? I mean, I don't know. What's the usual way to probe the degradation? Because rheology certainly can help, but as you just mentioned, I fully agree with what you say. It's not enough. So what else can you do to probe the degradation?
Using rheology?
No, not using rheology, using another technique. Like, for example, molecular probes like FTIR or NMR or anything like this.
Here I use the infrared spectroscopy to quantify it, and the size exclusion chromatography.
Yeah, you're right. Yeah, SEC. Yeah, you show the result. It was very convincing. Okay.
But so, are you saying that maybe another study of this to quantify this degradation could be interesting?
I think that SEC is very convincing. Actually, it's really, really clear that you had a decrease of the average molecular weight. But yes, maybe NMR or FTIR. I don't know if you can really see something. It really depends on the chemistry of the system. I don't know if you create some peculiar ends. If your ends, once you have the degradation, if they have some chemical group which are typical for the degradation or not. If it's not the case, I think it's difficult to see the degradation with molecular probes. So yeah, I think SEC is a beautiful idea. It's really cool.
Yeah, maybe try other techniques can be faster than size exclusion chromatography, or
yeah, maybe, but I think it's really good like this. You're right, SEC.
So for the biaxial bending setup, no, it's from Sarah, but Sylvain kindly let us to do this kind of test. And the 30. What's the mysterious bioglass surface made of?
You replied to the question already. So sorry, I was not paying attention enough. So
okay.
It's full of silicon oxygen minus, right? And this is why it's highly reactive with the polymer.
Yeah, and this is because the here there's a part of polymer who stacks the bioglass surface, and maybe it's because of this reaction we hydrolyze the PLI, who allows to have a better adhesion for the bioglass, and who can explain also because why the bioglass of S53P4 shown a better tensile strength than hydroxyapatite.
Okay.
What about composition structure of different bioglasses linked with the degradation behavior?
Maybe I can precise my question, because you show very complex composition of your different bioglass at the beginning, if I remember. Maybe I lost the point, but what is it? Is it a mix of powder, or it means that each particle is a mix of different oxide? It's hard to have an image of these materials for me.
So I don't prepare these bioglasses, but it's a particle who contains all these compositions in these ratios.
Okay.
And it's made by, I think, solid gel.
Okay.
Yes.
Solid gel, yeah. Okay.
And high temperature. And yes, there's different compositions, and maybe it's because there's one of them who increased this degradation. That was also studied by Eloise, who developed new bioglass during her thesis. I'm showing here, showing a better response. And she modified the bioglass composition.
Mm-hmm. Well, it was already complicated for me when Eloise did that, but okay. So it's the same bioglass. Mm-hmm.
Okay, thank you, Florent, for the questions. Xavi, also, thank you again. Maybe we can have maybe a few last questions. If someone has a last question.
Yeah, I did ask in the chat whether or not we do have that biaxial bending test. Where did you perform those tests, Xavi?
At Sarah pencil room. Yeah. It's a really small setup, and Sylvain told us that this kind of setup could be interesting to try our discs made by injection or other process.
Any other questions? No? Okay. So I will close the recording and